Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 7, Lesson 7 on the zero product law. Now you've seen the zero product law in Algebra 1, probably a little bit in geometry as well, and we've talked about it in this course, both in Unit 1 and in this unit. So let's jump right into it. Products equal to zero. You've now solved quadratics using the method of completing the square. That was the last lesson. Another technique that we can use to solve certain quadratic equations takes advantage of a property of factoring and the number zero. Let's bring that right up to the top, the zero product law. The product of multiple factors will be equal to zero if any one of the factors is equal to zero. All right, now the zero product law can be framed in many different ways, all right? But zero and product are exceptionally important words. When we've got something written as a product equal to zero, the only way that product can be equal to zero is if one part of the product is equal to zero. There is no other number like that. That's not true of the number 1, it's not true of the number 12, it's not true of the number 100, right? If I've got two numbers whose product is 12, one of them certainly doesn't have to be 12. If I have two numbers whose product is 100, one of them doesn't have to be 100. But if I've got two things that are multiplying to be zero, one of these things has to be zero, and in fact, if either one of these things is equal to zero, the product will be equal to zero. So let's see how we can do that in exercise number 1. Solve each of the following equations for all values of x. Awesome. So again, the idea is very simple. If I've got x plus 7 times x minus 3 is equal to 0, that will be solved if either x plus 7 is equal to 0 or if x minus 3 is equal to 0. And then that allows us to solve two very easy equations. X plus 7 is equal to 0. Of course, I can subtract 7 from both sides, and I get x equals negative 7. If this looks familiar, it should. We were just doing this a couple lessons ago. If x minus 3 is equal to 0, I can add 3 to both sides, and I can get x equals 3. All right. Now, in our previous lessons, both in this course and in Algebra 1, these were typically the kind of answers we got, answers that were whole numbers, right, or integers. They didn't have any fractional parts. But of course, that doesn't have to be the case. Let's take a look at letter B. Here we have 2x minus 5 times x minus 4 is equal to 0. And again, I just really want to hammer home, right? This equation will be satisfied for any value of x that either makes 2x minus 5 equal to 0 or that makes x minus 4 equal to 0. And there can't be any other value of x that will do the job because any other value of x won't leave us with part of a product that's equal to 0. So now we can say 2x minus 5 is equal to 0 and x minus 4 is equal to 0. I'm going to do a little dashed line here. Now 2x minus 5 equal to 0, that one's just a slightly more complicated equation, right? It's a two-step equation instead of a one-step equation. But that's the worst you'll ever look at in these kind of cases, is a two-step equation, right? So we get x is equal to 5 halves, right? And of course this one is simple. This is just our one-step equation. Add 4 to both sides, and we'll get x is equal to 4. Now, in our last one, let's take a look at that. We have 4 times 3x plus 2 times 4x minus 3 is equal to 0. Now, in this particular problem, right, we actually have three parts of the product. The number 4, the expression 3x plus 2, and the expression 4x minus 3. Again, any value of x that makes 3x plus 2 equal to 0 or 4x minus 3 equal to 0 will be a solution to this equation. So pause the video now and see if you can figure out those two solutions. All right, well, we can take our 3x plus 2 and set it equal to 0. Subtract 2 from both sides, we'll get 3x is equal to negative 2. And divide by 3 on both sides, and we'll get x equals negative 2/3. And another two-step equation, 4x minus 3 is equal to 0. Add 3 to both sides, we'll get 4x is equal to 3. Divide both sides by 4, and we'll get x is equal to 3/4. There we go, right? And either one of those will be a 0. Or will they? Let's take a look at exercise 2 really quickly. In exercise 1c, why does the factor 4 have no effect on the solution set of the equation? Well, let's actually take a look for a moment. Let's use, of these two, I don't know which one's a little bit more scary. Let's use the number 3/4 for a moment. Let's take that solution and let's substitute it into the equation. Let's see what happens. It's going to be a little bit ugly. 4 times, whoops, let's try that again. 4 times 3 times 3/4 plus 2 times 4 times 3/4 minus 3, right, is equal to 0. Let's see if that checks. Well, for a moment, I'm going to leave that parentheses alone. Well, maybe I'll work with it a little bit. That's 9/4 plus 2. Here, that'll cancel, and that'll be 3 minus 3, question mark. Why not? I've got 8/4 and 9/4, which is 17/4, and 0 equals 0. And now, let's take a look, right? I've got 4 times 17/4. Now, those 4's cancel, but that's totally irrelevant, times 0. And the plain fact is, right, as long as one of these two things, or as long as any one of these three things was equal to 0, right, then we were going to get a solution. The 4 really has nothing to do with it, right? This thing is still going to be a 0 because we've got, right, one of the factors equal to 0. So the 4 makes no difference because it can't be equal to 0. Right? It doesn't have any effect. And I like to point that out to students because sometimes what will happen is, they might take the two solutions and then say, well, there's a 4 sitting there, so maybe I have to multiply them by 4, or maybe I have to divide them by 4, or something like that. And that's totally not the case, right? The zero product law basically says, as long as one of these 3 factors is equal to 0, then the whole product will be equal to 0. Well, 3x plus 2 can be equal to 0 when x is negative 2/3, and 4x minus 3 can be equal to 0 when x is equal to 3/4, but the number 4 just can't be equal to 0. It doesn't have any effect on whether or not these two things can be equal to 0, right? Not at all. So we don't even have to worry about it. And we will see little factors like that every once in a while, especially if we've factored out a numerical GCF. Let's keep working with the zero product law. Factoring to solve. The zero product law can be used to solve any quadratic equation that is factorable, i.e. it's not prime, and is set equal to 0. That's why I really emphasize knowing the name of the law. It is the zero product law, and that implies 2 things. We've got to have a product, and that product has to be equal to 0. Let's take a look at exercise number 3. Solve each of the following quadratic equations using the zero product law. Awesome. So in our last example, right, all of our equations were already written as products. In this particular example, none of them are. All right. Now, what does it mean to write something as a product? Well, it means that we have to factor it. So I take a look at letter A. Let's take a look at that one. We have x squared minus 11x plus 24 is equal to 0. So we need to factor this simple quadratic, right? And this simple quadratic, we're looking for 2 numbers, right, that have a sum equal to negative 11 and a product equal to positive 24, right? Those 2 numbers are negative 3 and negative 8, right? Negative 3 times negative 8 is positive 24, and negative 3 plus negative 8 is negative 11. So we can now factor this quadratic as x minus 3 times x minus 8 is equal to 0. At that point, of course, now we have an equation that looks identical to the ones that we had in exercise number 2, or exercise number 1, not number 2. And we can take each of these factors, set them equal to 0, and we can solve probably in our head. This one's going to be x equals 3, and that one's going to be x equals 8. Now, in the remainder of our exercises here, B, C, and D in number 3, they all involve slightly different types of factoring. But we've been doing factoring for a while now, so what I'd like you to do is I'd like you to tackle letter B. Now, letter B is obviously a little bit harder than A because it's a trinomial whose leading coefficient is 3 instead of 1. See if you can factor that, and then if you can, set each of the factors equal to 0 and solve for the values of x. Pause the video now and take a few minutes to do that. All right, this is one of those ones that we're going to use the AC method of factoring on. So the first thing I'm going to do is find that product. Of course, 3 times 10 is 30. And I then need a sum of 11, right? The two numbers that have a product of 30 and a sum of 11 are 6 and 5. 6 times 5 is 30. 6 plus 5 is 11. That means now I can take this quadratic and I can break up the 11x as a 6x plus 5x. Right? Plus 10 is equal to 0. I'll now factor this by grouping, which means I will factor a 3x out of that, and I'll factor a 5 out of that. And finally, I can now factor an x plus 2 out of those common, more complicated expressions. And I'm left here. Now that took me a little while to get all the way to the point where I started in exercise number 1. But once I'm at this part, right, then I can create two very simple equations. X plus 2 is equal to 0, and 3x plus 5 is equal to 0. And when I do that, in this situation, I'll get x is equal to negative 2. And in this situation, and I actually encourage my students to try to solve even the two-step equations in their head, right? Because, you know, I think probably everyone at the Algebra 2 level can look at x plus 2 equals 0 and get x equals negative 2. 3x plus 5 equals 0 is more challenging, but if you just think about it, you're going to subtract a 5. That's going to leave you with negative 5. Then you're going to divide by 3, and that's going to leave you with negative 5/3. I contend that you really should, at this level, probably be able to solve two-step equations in your head, as long as they're not too messy, right? All right, so now, in C and D, we have additional types of factoring. What I'd like you to do is pause the video now and see if you can solve both C and D, right? Think about the types of factoring we have. We have GCF factoring, difference of perfect squares, simple trinomials, the AC method of factoring, and we also have factoring by grouping, which comes up when we do the AC method. Pause the video now and see if you can solve letter C and D. All right, well, letter C is a great example of factoring using the difference of perfect squares. So I've got 9x squared minus 1 is equal to 0. I can factor that as 3x minus 1 times 3x plus 1. So that's the difference of perfect squares. That gives me 3x minus 1 is equal to 0. And 3x plus 1 is equal to 0. In this one, if I add 1 and then divide by 3, I'll get x equals 1/3. And this one, if I subtract 1 and divide by 3, I'll get x equals negative 1/3. Now, before we move on to letter D, I do want to make a comment on letter C. All right, letter C can certainly be solved by factoring, and here it is. But letter C, notice, does not have an x to the first term in it. There's no x to the first term, which actually means we could solve this one using inverses. So just for a little sidebar here, if I took this thing and all they said to me was solve this, they didn't say solve it by factoring, I probably wouldn't solve this by factoring. I would add 1 to both sides. I'd get 9x squared equals 1. I'd divide both sides by 9. I'd get x squared equals 1/9. And then I'd take the square root of both sides, giving me both a plus and minus solution, which would be the plus and minus square root of 1/9, which would be plus or minus 1/3. And of course, that is exactly what we got right here. So it's kind of nice to see two very different methods for solving an equation result in exactly the same answers. If they resulted in different answers, that would be kind of frightening. All right, let's take a look at letter D now. I'm going to write this one a little bit bigger right here. It's 5x squared minus 30x equals 0. Now that's not the difference of perfect squares. It's certainly not a trinomial. What it is a simple GCF, right? I look at the 5, I look at the 30. I can pull a 5 out of both of those. I've got an x squared and an x to the first, so I can pull an x out of both of those. And this factors as 5x times x minus 6 is equal to 0. Now, you can think of that 5 being attached to the x, or you can think about it separately. It doesn't really matter. You know, some people would like to think of it kind of like this, and that's probably the way I'll sort of like consider it. Now, remember, either 5x will be equal to 0 or x minus 6 will be equal to 0. This one is a piece of cake. X minus 6 is equal to 0. That's x equals 6. But surprisingly enough, I find a number of people that will then get this one wrong, and they'll say x is equal to negative 5. But think about it. If you put negative 5 into this parentheses, you'd have 5 times negative 5, which would be negative 25. I need to make it equal to 0, not equal to negative 25. And in fact, it wouldn't be negative 5, even though I desperately apparently want to write a negative 5 there, because we would undo that multiplication by division, and 0 divided by 5 would just be 0. And now that makes sense, right? Because if I put 0 in here, I get 5 times 0, which is 0, and then times I don't care would give me 0, right? And I really don't care. I mean, it would be negative 6 if I put 0 in here, but I don't really care. As long as that thing's 0, the whole product will be 0. Similarly, if I put 6 into here, I'd get I don't care, and if I put it in here, I'd get 0. So I don't care times 0 is still going to be 0. All right, let's keep going. The zeros of a quadratic function. We can use the zero product law to reveal the zeros of a quadratic function if that function can be factored. All right? If the function can't be factored, then we've got to use things like completing the square or the quadratic formula, which we will eventually get to, just not in this unit. Let's take a look at exercise number 4. The quadratic function f of x equals x squared minus 4x minus 12 is shown graphed below. Letter A, state the zeros of the function by inspecting the graph. All right, this should be easy enough. Pause the video right now and tell me what the zeros of the function are. Right, well, they're simple, right? The zeros of a function are where the y, or the output of the function, is equal to 0. That's going to be here at x equals negative 2, and it's going to be here at x equals 6. Let me put those in red, right? So they're right here and right here. I'll even write them down in red. X is equal to negative 2, and x is equal to positive 6. And then I'll go back to blue. All right. Let's now take a look at letter B. Find the zeros of the function algebraically. All right, finding the zeros of any function, whether it's a quadratic function, a linear function, or anything else, right, is straightforward from sort of the first step perspective. I need to set the output f of x equal to 0. So in other words, right, whenever we're looking, whenever we're looking for the zeros of a function, right, we want to set f of x equal to 0. Not x equals 0, that would be the y-intercept, but f of x is equal to 0. So we want to solve that particular equation. Pause the video now, right? Do a simple trinomial factoring on this and solve for the zeros. All right, well, pretty easy, right? If we want to think about sum and product, we have a sum equal to negative 4, and we have a product equal to negative 12. Those are going to be negative 6 and positive 2 will be the two numbers, right? We can now then factor that as x minus 6 times x plus 2. I can then take x minus 6 and set it equal to 0, and I'll get x is equal to 6. X plus 2 is equal to 0, and x will be negative 2. And that, of course, is exactly what we saw in the graph. Here we've got x equals negative 2. Here we've got x equals 6. So if we can factor a quadratic function, we can easily determine what the values of its zeros are, its x-intercepts, probably just by inspection, especially when it's a simple one like this. It's like, oh yeah, sure, 6 and -2. A little bit more difficult if they're fractional. All right, let's do it. Exercise number 5. Determine the zeros for each of the following quadratic functions algebraically by writing the function in factored form. All right, well, what I'd like you to do is pause the video now, see if you can do letter A, then we'll go through it, and then we'll have you do letter B, which is a little bit more challenging in terms of the factoring. All right, let's do it. So, I'm really trying to solve this equation. Whenever I'm looking for the zeros of a function, I set the function equal to 0, right? I've got a sum equal to 7. I've got a product equal to -30. What are going to be those two numbers? Those are going to be 3 and 10, but I've got to make the 3 negative and the 10 positive. That means I can now factor this as x minus 3 times x plus 10 equals 0. X minus 3 will be equal to 0, and x will be 3. That's one of the function's zeros. X plus 10 is equal to 0, and x equals -10. And there are my two zeros. Awesome. I love it when a quadratic has a leading coefficient of 1, right? Very, very easy to factor those. We just have to think about that simple sum and product, and then we have them. Letter B, this one's going to be a little more challenging with a leading coefficient equal to 8, right? Now you're going to want to do that AC method of factoring. Pause the video now and see if you can figure out the two zeros of g of x. All right, so we've got a product equal to 8 times 3, or 24, and a sum equal to -10. What will we have there? Well, it looks like we're going to have a 2 and a 12, and we need to have, no, that's not going to do it. I was going to say -2 and -12, but that's not right, right? It would give me a product of 24, but it wouldn't give me a sum of -10. And then I thought, I was thinking +2 and -12, right? Because that would be a sum of -10, but 2 times -12 isn't +24. So it's not 2 and 12. In fact, right, it's -4 and -6. But I almost fell for it, right? I was almost like, oh yeah, 2 and 12. That'll get me that 24. And, if I subtract the 2 and the 12, I'll get that -10. But I need to have a positive product and a negative sum, so my two numbers have to both be negative. And -4 times -6 is +24, and -4 plus -6 is -10. All right, that will now allow me to take my x squared minus 10x plus 3 equals 0, and it'll allow me to break it up as x squared minus 4x minus 6x plus 3 is equal to 0. Let me move that out of the way. We now can group with a little plus sign in between there. I'm going to pull a 4x out of both of those. That's going to leave me with 2x minus 1. And here, I'm going to have to pull out a -3 from both of these, also leaving me with a 2x minus 1. Remember, the method of factoring by grouping only works if these two binomials at the end are the same. I can now rewrite this as 2x minus 1 times 4x minus 3 is equal to 0. We're going to have two fractional answers now, one of them from 2x minus 1 equal to 0, one of them from 4x minus 3 equals 0. By adding 1 to both sides and then dividing by 2, I'll get x equals 1/2. And by adding 3 to both sides and then dividing by 4, I'll get x equals 3/4. All right, that's it. And that's almost the hardest one you can possibly see if the degree of the polynomial is 2, if we've got an x squared as opposed to an x cubed or something like that. All right, rearranging equations. It is critically important to be able to solve quadratic equations that can be factored. Sometimes you will need to rearrange a quadratic equation so that it is equal to 0 before you factor, right? Every equation we've worked with so far has already been set equal to 0. But many times that doesn't have to be the case. So what we're going to do is we're going to end the lesson today by looking at a few exercises where we have to get the equation equal to 0 first. Exercise number 6. Solve each of the following quadratic equations for all values of x by first rearranging them so that they equal 0. All right, letter A. X squared plus 3x minus 14 is equal to negative 2x plus 10. Now to begin with, on this particular equation, I see that the left-hand side's got an x squared and the right-hand side does not. That means what I'm going to try to do is move everything from the right over to the left, okay? And then I'll have it equal to 0. In letter B, I've got a 3x squared here and a 1x squared there, which means I'm going to do the same thing as opposed to like moving it all over here where I would end up having a negative coefficient on my x squared. If you can do all the movement in one step, I would advise it. So let's take a look at how that's done in letter A. Okay, so we've got our x squared plus 3x minus 14 equals negative 2x plus 10. That means I'm going to have to add a 2x to both sides to remove that negative 2x. Ugh, that just does not look like a plus 2x. I'm going to have to add a 2x to both sides, and then I'm going to have to subtract a 10 from both sides. I can do that all at once. If you need to do it in 2 steps, that's completely okay. Nothing now combines with the x squared, and I have 3x plus 2x, which gives me 5x. I have negative 14 minus 10. Be careful there. That's going to be negative 24. And then the whole point is that on this side of the equation, I now have it equal to 0. All right. At this point, we can now factor, set each factor equal to 0, and solve. Pause the video now and see if you can finish off this problem. All right, I'm looking for 2 numbers that have a product of negative 24 and a sum of 5. Right, so my product and my sum, those 2 numbers are 3 and 8, where I think I need to make the 3 negative and the 8 positive. Notice I do have to think about that a little bit, right? I have to be like, all right, I think it's 3 and 8. Okay, it gives me that negative product, positive sum. So then I'll factor as x minus 3 times x plus 8. Get that all equal to 0. I'll have x minus 3 equal to 0, which means x is equal to 3. I'll have x plus 8 is equal to 0. And that means x is equal to negative 8. Great. What I'd like you to do now is pause the video, try to rearrange this equation so it's all equal to 0, then take the resulting equation, try to factor it, set each factor equal to 0, and solve. See what you can do on that problem. All right, let's do it. So step 1, I've got to get the equation equal to 0. We cannot do the 0 product law if the equation is not equal to 0. Here we go. So I'm going to subtract an x squared. I'm going to subtract a 3x. And then I'm going to add a 2. Okay, sorry about the messiness there. 3x squared minus 1x squared is 2x squared. 12x minus 3x is positive 9x. And negative 7 plus 2, we got to be careful here, is negative 5. That's equal to 0. Great. So that's step 1. Step 2 is recognizing what kind of factoring we have to do. And again, you've got to be thinking, I've got GCF, difference of perfect squares, simple trinomials, more complicated trinomials, and this is a more complicated trinomial, right? Because the leading coefficient's not equal to 1. So I'm looking for 2 numbers whose product is equal to negative 10, right? 2 times negative 5, and whose sum is equal to 9. And that one's kind of interesting because the 2 numbers are going to be negative 1 and positive 10. Negative 1 times positive 10 is negative 10, and negative 1 plus 10 is positive 9. So I can now break that 9x up into a 10x minus x minus 5 is equal to 0. I'm now going to group my terms kind of like this. I can factor a 2x out of the first 2. And this is interesting, I'm going to factor a negative 1 out of the second 2. I have to do that to get that x plus 5 common binomial factor. At this point, I now can factor an x plus 5 out of both of them, leaving me with x plus 5 times 2x minus 1, setting my x plus 5 equal to 0 and my 2x minus 1 equal to 0. Here I simply need to do a one-step equation, which gives me x equals negative 5. Here I'll add 1 and then divide by 2 on both sides to get 1/2. All right, and that's it. So let's summarize. The zero product law is undoubtedly one of the most important ideas in all of math, bar none. I would definitely put it in my top 5. And it's important because there are so many equation solving sort of methods that boil down to the zero product law. The idea being, if we can factor an expression that's set equal to 0, then we can take each one of the factors and set them equal to 0. And what that really does, if you think about everything that we've done today and what you did in Algebra 1, is it takes a more complicated equation, one that involves an x squared here, right? And it creates two very simple equations based on that one. Now it only works if two things are true. The equation is equal to 0 and the expression that's equal to 0 can be factored. The zero product law is just, you can't use it if you have a prime polynomial or a prime quadratic, one that cannot be factored. But as long as it can be factored, then setting each one of the factors equal to 0 and solving will give you all the values of x or t or n or whatever that solve the equation. We're certainly going to get a lot more practice with the zero product law as we move through this unit and through this course. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.